Expanding lunar exploration presents unique and exciting challenges for establishing infrastructure on the moon. From aluminum to iron and electrical wiring to structural components, we will have to extract and manufacture most of what we require on the moon to make exploration feasible. For nearly a century and a half, Colorado School of Mines has been creating and implementing solutions for extracting and processing raw materials.
Colorado School of Mines is presenting LAMPP, the Lunar Alloy Metal Production Plant, a conceptual lunar reactor which uses molten regolith electrolysis technology. Our objective is advance the knowledge about the ceramic behavior under the extreme conditions of the process. We tested several materials under high temperatures and under the chemical aggressive behavior of the lunar signal.
The first static dwell test was designed to address the feasibility of specific refractory materials for use in our MRE reactor. The refractory materials chosen include boron nitride, aluminum, molybdenum, and silicon carbide. These refractory materials will be submerged in a regolith melt with both anorthositic and basaltic compositions at temperatures of around 1300 degrees Celsius for durations of roughly 1 hour. The steel housing was custom designed in-house at the Colorado School of Mines. Analysis of the results after the test was complete showed that alumina and boron nitride were not prime candidates for use throughout the entire reactor and removed from prime consideration for remaining tests over the course of the project.
This test was the second static dwell and also the static holding of the cooling of the refractory crucibles. For this test, 2 silicon carbide and 2 molybdenum rods and crucibles were tested. 1 rod and crucible of each was coated with a boron nitride, and the other was uncoated. 5 layers of aerosol-based boron nitride were applied, ensuring each layer was dried before the next application. So additionally, 2 additional crucibles were tested to evaluate their performance. These were uncoated boron nitride crucibles. So the team decided to test the boron nitride as a coating because it was commonly used in high temperature ceramics due to its lubricating properties. And that's also what allowed the material to easily be removed from the moldings. This experiment tested whether boron nitride reacted with silicon carbide or the molybdenum when coated, and also helping if it had any refractory longevity. So like in dwell test 1, the rods were cast into the steel housing and then submerged into a molten regolith simulant for 1 hour. After removing it, the team observed that all 4 rods remained within the housing and appeared to maintain most of their section. The rods were then left to cool and then were set aside for post-mortem microstructural characterization. And then the remaining molten regolith simulant was then poured into the crucibles and left to cool in ambient room temperatures. After these crucibles were cooled for 24 hours, the glassy material was easily removed, as you can see here, and from the silicon carbide and molybdenum crucibles, but not from the pure boron nitride crucibles. The boron nitride coating on the silicon carbide and the molybdenum crucibles showed scorching, but all 4 appeared to have no deterioration or section loss. These results confirmed that the selected material performs as expected and was to be further tested for dynamic processes and to understand the movement of flowing molten material and any additional corrosion effects.
The dynamic dwell test was designed to evaluate loss of material from refractory rods due to the rotation of the rods while submerged in a regolith melt. This was accomplished by outfitting our original steel housing with bearings and change-driven sprockets. These rods could be rotated either manually by hand or with an offset motor as needed. 2 primary materials were selected for the dynamic test: silicon carbide and molybdenum, each with a thin coating of boron nitride applied evenly across their surface. As opposed to the original dwell tests, the dynamic test lasted only 5 minutes. However, that short test showed immediate results, with the boron nitride disappearing completely from the molybdenum rod. Once dwell testing was complete, the regolith melt was poured across 2 sets of matching silicon carbide and molybdenum tiles. Similar to the dynamic test, 1 set of these tiles was coated with boron nitride. The pour test was conducted in order to measure the flow rate of molten material across each refractory media, with thermocouples tracking the heat profile of the refractory tiles, and then the tiles then being examined for damage once testing was complete.
Following the static dwell test number 2, a cross-section of each rod was taken for characterization and microstructure analysis of each rod's surface. A control sample of each rod was taken from a non-regolith exposed point on each rod and a regolith exposed point. These samples were section mounted and ground and then polished for characterization using an optical microscope in the bright field. They were then gold coated for further study in a scanning electron microscope equipped with energy dissipative X-ray spectroscopy. These tests were taken to understand surface morphology after exposure to molten regolith.
Here I have one of our test samples ready to use in the electron microscope. The sample was sectioned and polished after we exposed it to molten regolith, and we can resolve microscopic features and elemental composition with this machine right here. This is the specimen chamber, where I can insert our sample, close it up, and let it come down to vacuum for observation. Now that our pressure is sufficiently low and our sample is in position, we can turn on the electron beam and observe our sample. We can now identify features that are invisible to the human eye.
The results of this test indicate that the exposed surface of the silicon carbide sample appeared to be minimally impacted by the corrosive effects of the molten regolith, but removal of the boron nitride did occur. For the molybdenum samples, considerable degradation on both the coated and uncoated surfaces was observed. Unwanted iron alloy and regolith melt from the regolith melt and spoliation were also observed. These results suggest that the molybdenum may not be a reliable material for long-term use in an MRE reactor system. The results from our verification testing appear to indicate that silicon carbide is a good candidate for a lunar MRE reactor material. The performance of silicon carbide also was improved by the addition of a boron nitride coating. However, the team also identified that the carbon-based refractory are at risk for a reaction with oxygen in an MRE environment, and this could generate carbon dioxide. However, through our analysis, our team also verified that there is no thermodynamic risk with the boron nitride reacting to oxygen. Thus, the team suggests that using a silicon carbide and boron nitride composite refractory structure should be considered for a lunar-based MRE reactor, like the LAMPP system that we have proposed. Any subsystem that makes contact with molten regolith should consider this layup to increase performance from the lifespan of the overall system. However, the suggested composite system doesn't use spray or paint coatings of the boron nitride, but a fully replaceable inlay, meaning the boron nitride will act as a wearing surface and the silicon carbide will act as a physical structure for the refractory. The team recognizes that the suggested refractory technology is likely in a TRL 3 to 4 level, and we suggest that testing of a prototype composite system be conducted in a vacuum environment with regolith simulant or compositional slag oxides as the next laboratory testing step. And this would continue the path to flight development for this material.